So we're still on time evolution, and I know I spoke at length about, I know it probably was hyper confusing about why things evolve in time, but let me just remind you of, so if we have a state that is an eigenstate of A, and of course that is the definition of an eigenstate, and a Hamiltonian, which is the only thing that's the one that's actually important. So it returns an energy. Then, of course, that, that state has a certain expectation value, which is actually a prime, right? And that doesn't matter whether you time evolve or not, which of course is using the language that we've been covering, where the states evolve in time from t0 to t. Okay, so in other words, absolutely nothing is happening. Now, if one of the things that you'll see more and more of is why, if I have operator B that does not commute with A and does not commute with the Hamiltonian, and if A commutes with H and B does not commute with A, then I think B doesn't have a choice but not to commute with H. Now, right now, I know this doesn't seem like, well, okay, so what? So what will be more apparent in a little bit more time. Still nothing changes. So I'm time evolving, you know, if I looked at the expectation value of the time evolved state, it's the same as the non-time evolved state. And God knows what that is. If they don't commute, then this, anyway. So the point of this is, a little dash, I need to have a little dash, sorry, a little dash, that's important. I had a dash. Book is obsessed with little dashes. So the big picture, if a state is not, it is an eigenstate of a Hamiltonian, nothing about it changes. It is totally non-dynamical. No matter what operator no matter what property you're querying, nothing changes with time. Now that's what instigated my long, I kind of went off on some weird tangent about, which is true, that it's an odd result because we like to think of things as being in ground states. You know, hydrogen atoms are in the 1s state, unless we shine light on them, and then they can be in excited states, sure, that's fine. But for the most part, I think of hydrogen out in this whole universe, which has a lot, I'm sure it has a lot of hydrogen atoms. It has a lot of H2, but I'm sure there's hydrogen atoms just randomly floating around between nebula and whatnot. And I like to think that they're still dynamical, and I'm sure they are, but they can't simultaneously be ground states of the Hamiltonian. And I proposed a resolution saying maybe you don't really know what the Hamiltonian is, and that may have been hyper confusing, and I'm actually going to bring that up over and over again because that's really how you want to think, but I know that that's confusing right now. It'll be less confusing as we move on and we get into perturbation theory. So I'm even going to bring it up again later today. All right, now again, eigenstates of the Hamiltonian don't involve in time. So how is anything happening, right? If the world is composed of molecules and atoms in their ground state, then the universe is a frozen crystal. Nothing is happening, and yet the exact opposite true. Almost everything is moving. Everything is dynamical. So how the hell does that? How does anything happen given what I've just shown? Okay, now the stuff I talked about earlier, that's a very hard pill to swallow. But let me give you an easier one first, and then I'll get back to that more difficult concept of, you know, like I say, there's more to a hydrogen atom than just the Coulomb operator between an electron and a proton, which is how you solve the hydrogen atom energy Anyway, and again, I'm already going off in a tangent. Okay. All right, now, here's a way that you can make things evolve in time, which is to perturb them, to put things in an excited state. So let me cover that one. This is easier to follow, and we already have some good examples. Okay, now the way that would work is that, as usual, this nebulous state alpha, and I'm using this expression that I came up with. Book uses dashes, and I'm using this a to the n, which I think is a hell of a lot easier to follow. And again, at this point, you're hopefully looking at that saying, oh yeah, that's a resolution of the identity. It's good for time to pass because you see something like this, and hopefully at this point you're just completely comfortable with this. And you know that this is an inner product, so it's a number, it's the overlap of the alpha state with whatever basis set we're in. So this basis set is the bunch of particle in a box states. Okay, so what I'm going to show you is that, therefore, if you time evolve alpha, again, still using this book notation, that they will actually change later on, and I'll faithfully reproduce that, point that out. You know that this is a coefficient. This coefficient, what it does is it changes in time. Okay, so this is, so when we have a state and we resolve the identity, and we recognize that's a number, some coefficient that represents how much of alpha is in the N1 state, the ground state, the N2, the first excited state, and N3, second excited state. One way to think about time evolving that state is that these coefficients evolve in time. That's a really nice way to do time resolved, time in quantum mechanics. And when we do time-dependent perturbation theory, we're going to use that representation, which is particularly nice. Okay, now what I'm going to do, keeping that in mind, now I'm going to evolve, I'm going to look at state B, and B, the expectation value of B over time, and I'm going to use this type of representation to do that. Okay, so still, let's say still B and A do not commute. So I'm still talking about the same B. And you'll see why that's important. Okay. Now the expectation value of B, which now we're going to use time evolving states, like I've just shown. And let me be very formal with that. I'm going to write, okay, I'm going to write this in a non-time dependent form because here's that time evolution operator, right? So this is how we often see, right? This is the unitary transformation that we often see when we're changing things around, changing the representation of turning a state into something else. It's always a unitary operator. So, and I'm adding a second resolution of the identity for the other side, and so I have to have a little dash there. Okay. So again, to do this, I did two resolutions of the identity. What you're seeing is me turn the time evolved state using this, but I have the unitary operator, of course, the adjoint operator on the draw, and the unitary operator, the regular operator acting on the ket. And now you should know, of course, that what the heck does this look like? This is incredibly easy. This is e to the I Hamiltonian operator t, but the Hamiltonian operating on the state just returns the eigenvalue, so that's e a to the n prime t over h bar. You know what, actually I need to, so the book is still using T naught, and after, in a couple of pages, it stops using T naught, it just says T naught is 0. I never give myself enough room. Okay, anyway, so there we go. Sorry, n prime. I'm just writing the same thing. Okay. So there you go. And then on the other side, I have to do this as well. And I've got C, A, B, N, complex conjugate because it's a bra. And then I've got A to the N, and then E to the minus. No, there's a minus here, there's a minus there, and then it's plus on the adjoint is plus. I-E, A to the N, no prime, T minus T naught, all over H bar. Sorry, no, that's kind of hideous. But the main thing is what this reveals. It reveals what the time dependent. It shows you what the way that the time dependent coefficients are. They're just the old coefficients that we've been working with times e to the I energy t over h bar, or if it's a ket, then e to the minus I energy t. So there's really not much to this. Now the thing is though, and one of the, again, the bigger lessons that we have to do is understand when can you manipulate operators around. And this is one of those times, you know, like as written, you can't just cause this operator to leap over the B operator and then cancel. You know, if I have U adjoint U, they cancel. And that's great. But you can't do that because there's this B operator in between. And if B does not commute with the Hamiltonian, then you absolutely, then for certain you can't do that. However, given how I set it up, I now have transformed those unitary operators into numbers, right? E to the energy is, even with an I in it, it's just, it's pi or something, right? So now what I do is I'm going to take all the numbers and I'm going to move them all over to the right. And the neat thing is that now I can take the difference in energy, and of course so there we go. And then you end up with double sum. Try that n prime, that's n. Okay, so big picture, I've time evolved the states with taking the state, having the operator on it. I just use this particular form for the state, and then the same for the bra. Remember that the unitary operator, instead of minus IHT, it's plus IHT. It operates so you get IET. Okay, then there are numbers, they can be manipulated. Okay, now here's where it gets funky. Since B does not commute with A, so B doesn't commute with A, and I'm always telling you that that is very meaningful, and it can mean several things. Therefore, A to the n prime, sorry, I have A to the n. Oh, I keep changing them. Sorry. Subscripts are superscripts. Looks like I never do it the same way twice. That's stupid of me. Okay. Is looks like an awful M. Not a delta function. Okay. So, now here's an example, by the way, in case that's confusing. If the a to the n are like plus and minus, then, you know, if then a is like sz, and that's diagonal, then b is like sx, which is not diagonal. Okay, so again, I want to just review all those terminologies, all those concepts. So, if you have a basis set that of an operator, and so it's like a basis set of SC, and so A is SZ, then the operator has no off-diagonal terms. So what that would mean here, let's say that we were doing A instead of B. What would happen is, if this was A, and these are the eigenkets and eigenbras of A, then if A to the n and A to the n prime are not the same state, then you get 0, right? So remember that A would operate on its eigenket, return an eigenvalue, and then you get those two states next to each other. And they have to be the same state because then they're 1, because they're normalized. But then, if they're not the same state, then they're 0. Remember, that also means that the integral of a wave function squared is 1. It's normalized. But the integral of a wave function of like an excited state times the ground state is 0. So they're orthonormal, right? Okay. Now, if that's the case, if this was the A operator, and then that makes this a parameter delta, and so what happens is that an prime and an are the same number, in which case that's e to the 0, which is 1, right? Which means that there's no time evolution, because time only appears here. So again, if that's A, then there's no off-diagonal terms, which is a fancy way of saying that an prime and an have to be the exact same state. Okay, but then that means these two different energies are actually the same energy, and when you subtract the same number from itself, you get 0, and e to the 0 is 1, and now there's no time evolution. Okay, but in this case, B can be off-diagonal. So you could have a plus and a minus, right? So you could have the plus state go through Sx and a minus state here and not get 0. And if that's the case, then that thing survives. And if that survives, there's time dependence to the expectation value, right? Because, anyway, what I just said, right? Okay, so you kind of follow that? All right, now let me give you an example, make that real solid, and I'm actually going to use spin states with spin. And it's also a bit of a walk down memory lane. So recall that we had AG atoms, and they have a 5s electron, and all the other electrons are paired. And back in the day, we had them go through the Stern-Gerlach experiment, and recall that the magnets are set up. That's the plus, and that's the minus. The first magnet was set up in the z direction. Okay, so that magnet basically gave us a Hamiltonian. Right? So the lower energy ones went up. It technically would be lower energy to be spin up. The higher energy ones went down. Anyway, and I'll define that. So the magnetic moment of an electron is E over mc. So I can see that this involves the theory of relativity. H bar over 2. Okay, that's the magnetic moment. Now, to know the effect of magnetism, you would dot that into a magnetic field. Now, given that I'm going to set it up this way, in h bar over 2, it's tempting to call that SZ. Right? So, what will happen is, therefore, the Hamiltonian, it's critical to remember that it's because I've set up a Stern-Gerlach in the z direction. Now, and again, this is electromagnetism, which even I don't remember. I actually did double check Wikipedia to make sure that these equations are correct. Okay, so it's the magnetic moment of the electron dotted into the magnetic field. Okay, well, we know S is going to spit out h bar over 2. But of course, it needs to be aligned with the magnetic field. So, given that I'm going to build the Stern-Gerlach up and down in the z direction, therefore the Hamiltonian is minus B over MC SZ operator, right? Because that gives plus or minus h bar over 2. Also, one thing to note, I just want to point out this to you. When you're looking up equations for whatever, you got to be crazy careful when it comes to charge, because the reason this minus is there is because the charge of an electron is negative, but positrons and protons are positive. So E, of course, is the charge of an electron in coulombs. If you look it up, it is inherently a positive number. It's just the charge of an electron. You have to know that if you see that minus sign, it's being there because of the negative charge. So if I saw this equation, I would get that. I would know to use the whatever coulombs is of the charge of an electron, and that minus is minus because the electron is minus. You could be tempted to make it double minus, right? You say, oh, but E for an electron is actually minus the number of coulombs, in which case now you've got minus minus, and now you've got it completely wrong. Be careful about this. This is one thing, and double check. Equations for stuff involving charge never make that clear. If they're careful enough, they did. And the way to make like the converse situation, like I described double minus, instead of an E, they use a Q. A Q for charge, in which case you wouldn't have that negative there. It would have, instead of an E, you'd have Q, in which case you put in minus E for an electron. If they've been careful and they use proper notation, that's how they would have done it. But a lot of people are going to screw that up. Anyway, I just want to point that out because it's something sometimes I spend a really long time on. Okay. All right, so if the Hamiltonian is basically the SZ operator times some constants, which I don't care about, then of course the SZ operator in the Hamiltonian, which is a function of that operator, it's just that operator times some constants, clearly they commute. And of course, plus minus are kets of SZ. I mean, by definition, plus minus are kets of SZ because we define them to be, but they also have to be kets of the Hamiltonian. And so if you apply the Hamiltonian, sorry, I forgot the little hat. If you apply the Hamiltonian to plus or minus kets, then what you get is minus plus h bar over 2 E B over MC. Of course, plus minus. So remember, I didn't have some spastic moment and wrote that backward. We think of the plus state as being the lower energy state, as being the ground state. And of course, that means it has a less energy, right? I know that's a little contradictory in terms of how we like think culturally, but technically, lower energy is good, right? So the negative energy is lower energy than the positive energy. So the energy difference is positive between the two states, and that makes the plus state the ground state. So anyway, it's a little subtlety there, but you want to make sure you keep track of that. Okay, now there's a neat trick What I want to do, when you have these two-state type problems, you can actually re-represent the Hamiltonian in terms of the plus energy and the minus energy. And that's really nice because that corresponds to a spectroscopic observable. And that makes a lot of this more meaningful. It's a little bit easier to write all this stuff down as well. Okay, so what happens next is, I'm going to remind myself. Okay, now hopefully you know that the difference between, say, an excited state and a ground state, ground state and excited state doesn't really matter, over h bar is an angular frequency. Let's see. 2 pi energy over energy time is 2 pi over time, right? So that's hertz times 2 pi, which of course is if it was just 1 over time, that's frequency, but 2 pi over time is angular frequency. Okay, so that's kind of obvious. And then if you just look at it, it ends up being minus EB over MC. And therefore, I can rewrite the Hamiltonian. As you see, this is just like a hell of a lot easier, so I'm glad to be able to do that. And therefore, the time evolution unitary operator is e to the minus I WSZ. And this is where the book drops T0. I'll write it just for the hell of it. Anyway, the book starts dropping T0 here, which you just call 0. So, tell you what, let's follow that because it really does get complicated. Call T0 equal to 0, drop it. So I thought it was very funky that the book always has T minus T0 up until this point, and then you never see T0 again. But I think they did that because it made some of those derivations we did earlier possible. It would have been kind of confusing not to have T0 implicit in some of those derivations. Okay, anyway, so that's why they do that. Okay, so therefore, let's operate on the plus state, and there's not much to it. E to the minus I, frequency T, over 2. Yeah, right, because what the operator, remember that the eigenvalue of the operator just, you pop it up here, and it's h bar over 2, plus h bar over 2. So you end up with minus I angular frequency T. Again, we're dropping to T0 over 2. Okay, so again, I went through this rigmarole because it actually makes this like way easier. I really like seeing that. That's like way easier to deal with. Okay. Now, this should be no mystery. I hope that you can answer this question if I was to ask, but I won't, because again, I know it is kind of new. What I'm going to do is operate on, what I'm going to do is I'm going to time evolve the state and project it into its time 0 self, right? So one of those times, that's one reason I record is that when you see this, you may be like, oh, okay, plus u that, but what is it? This is time evolved and projecting it into its time 0 state over time. And of course, this is a observable because I've taken the complex conjugate times itself. And speaking of which, okay, so let me do, I'm going to get the energy. Notice I'm leaving myself a lot of room. Yeah. Here, gives me that. And I'm writing this to the right because the ket is going to pass through it and hit the bra. Not that there's anything, that's just the number 1. Okay, but now I'm doing the complex conjugate, right, times itself. Of course, you remember absolute value squared is complex conjugate times itself. And, minus, I keep forgetting the minus, it's right there. Okay. Now the complex conjugate of this is e to the So remember, this times its complex conjugate, there's this times its complex conjugate, and what's all this? What's plus plus? 1. E to the minus I times e to the plus I. Remember, it doesn't matter what, it doesn't matter what operator. That's an eigenstate of the Hamiltonian. It ain't gonna do anything, ever. Right? So if this was minus, what would you get? 0. And there's no time dependence, right? It is behaving as itself forever, because there's no time dependence. If I said, well, wait a minute, does it ever point down? No, forever. It will never do that. It will never point up, it will always point down. That's what we get out of it. But this is exactly what I've been blabbering about the whole damn time. Okay, now we're going to make it more interesting. Let's do this. So again, this was the boring case. This is the eigenstate of the Hamiltonian not doing anything, and it's just another more rigorous demonstration. Okay, now, let's say that we do this. We have, let me draw a coordinate system. Let's say we have a plus state, and you can rotate that into the x plane. Okay, so let's look at, so now what happens? So now we're going to evolve, so somehow we've turned the plus state into the Sx plus state by some trickery. But you can actually do that with radio frequency pulses, by the way. Okay, so now what do we get? Okay, now we all know that the Sx plus is the plus state over square root of 2. The effective time evolution on this one is minus I wt over h bar. Oh, no, over 2, over 2. I've already operated on it. Sorry. Okay. Now the energy is negative, so the minus sign goes away. Okay. So again, the energy e to the Hamiltonian operator t over h bar blah 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 operates on each of these states. The state was plus over the square root of 2 plus minus over the square root of 2. That's the Sx plus state, and I'm hoping you remember that. So again, you can see that time evolution. The problem starts out relatively easy. Right? This should not be mind-blowing. Okay, now I'm going to do this. Let's do a spectroscopic we're going to do an observable. So I'm going to take an absolute value of the Sx state. Okay, so again, I'm going to take the Sx plus state, I've prepared it somehow, I'm going to evolve it in time, and I'm going to see how it changes with respect to its original self. Absolute value squared, because that's an observable. Okay, so what do you get? You end up with this. Okay, the bra is again, I'm praying that this is familiar to you. And I've got all these spin deals memorized. Okay, so there's the bra. The operator is, the action of the operator, I've already set it up. So then you go with e to the minus I wt over 2 over square root of 2. And again, draws and kets for spin are kind of fun. It's like a simple game, right? That one's minus, this one's plus, right? Yeah. Over 2, square root of 2. And Again, you play the FOIL game, which is actually easier than the type of quadratic equation, this or that you had in middle school. This is actually slightly easier due to the rules of Dirac notation and spin, expressions of spin and Dirac notation. Plus minus is 0, minus plus is 0, plus is 1, minus is 1. So this ends up, I need, sorry, that parenthesis was too big, it bothered me, and I need to remember that I'm going to take the absolute value. Okay, now you can work all through that, but let me just show you what you're going to get. E times I, t over 2, plus, and then all you do is you use, cosine plus I sine, cosine minus I sine. Okay, so again, throw some trig identities in there. I'm not even going to do that because at this point you really should not have a problem with that, I hope. There you go. Okay, so time evolution. In a magnetic field, this guy is perfectly still. But if you bend it over, which you can do that kind of stuff with radio waves, into the Sx plus state, at time 0, cosine squared is 1. So it starts out at time 0 in the Sx plus state, just like I said, because I dictated it to, but it will go away. And guess what? So the if you do this, so if it's not in the plus state, Sx plus state, it better be in the Sx minus state. So not, if you want to go through that whole rigmarole, then of course, as cosine phases out to 0, sine kicks in. So what's happening is, it's rotating, what's happening here? It's rotating around, going from plus to minus to plus to minus continuously. And there you go. So, now you've seen how time evolution can give you dynamics. It requires you to have some kind of Hamiltonian, a little bar magnet, and then you're going to have to act on it to displace it from the eigenstate of that Hamiltonian. Because while it's in an eigenstate of the Hamiltonian, nothing happens. And as much as we can work on this, ultimately the result is truly tragically boring. Nothing happens. Okay, now the last bit I want to show you, and this is kind of interesting. And let me ask you this. Is this are these the same thing? Now, we've just done this. Sx plus time evolved projected into Sx plus is right here. Is this the same thing as the Sx, what is that? Expectation value. Is that the same thing as the expectation value over time? Don't you think? Kind of? Doesn't it look like it should be?
I'm going no.
No, it's not. It's not, right? What you have to do, this, what's that? See, I get confused sometimes because I ask that because I get that confused. That is actually this. Sx plus time evolved draw. Then you gotta have the Sx operator. And then you have to have Sx plus also time evolved. That's what that is. Okay. Now, of course, the Sx operator, and I know we're out of time, so let me give you the result. Now, remember the Sx operator is this. And that's especially easy when you're working with, remember that any operator is an eigenvalue times one state plus the eigenvalue of the next state. Outer product. Outer products are, of course, operators. Okay. So that's the Sx. All right, so what you end up with is, and I'll do this next time. And T, that, of course, that T, I think you know full well, because this, I'm doing this time involved, ends up being h bar over 2 cos. And you can run through all this, and you know, I had you do that homework where I had you do a lot of spin operators, and so I hope that that's none of that's particularly difficult. Okay. Now I'll review. I'll start from here. I'll write out all the expressions. It ends up being just a lot of foiling, and I don't want to spend a lot of time on middle school algebra, slightly advanced middle school algebra. But again, what it shows is that when you take this state in an eigenstate and bend it over, you can see that it starts out h bar over 2 at time 0. But eventually it'll go to 0, and that's when it's rotated into the y direction, in which case now your plus sy goes here. Then sometime later it turns sx minus, when now cosine is negative. Sy, of course, will be 0, and then it turns sy negative, and then it goes back to sx plus. So it's rotating around and around and around. So it is dynamical. So you can get dynamics. You just can't be in you can't be in an eigenstate of the Hamiltonian. You have to be in a superposition of eigenstates of the Hamiltonian. As for how you do that, you do this trick. You act on it, or we'll talk a little bit more about other ways of doing it. Anyway, so you gotta go. But anyway, came out, this is not too bad, right?
No.
Yeah, when we get into, so yeah, I hope this wasn't too bad. It's just that what I want to get you to understand is though is why do things, I don't, you know, the world is dynamical without me having to prod it. Things are spinning around without me blasting it with radio waves. Why is that? Now, it's the reason I talked about last time, that maybe states aren't what you think they are because the full Hamiltonian is more complex. And again, that's a really important concept. That's really hard. That's why I'm going to bring it up every day for like the next till class is over. It's a powerful way to think.